Hi guys, my name is Myrto and today I'm going to present problem number 14, ruler trick. So let's get started. The problem statement states that when we place a ruler on the edge of a table and throw a ball at its free end, the ruler will fall, of course. However, if we cover part of it with a piece of paper and repeat the throw, then the ruler will remain on the table while the ball bounces off of it. We have to explain this phenomenon and investigate its relevant parameters. So let's get started. When the ball hits the ruler, part of the ruler on the table tries to lift, and the air tries to insert under the paper. Since the force is sudden, the air does not have enough time to enter under the paper, and a vacuum is created. The atmospheric pressure force on the paper is great, and thus it is not enough to compensate and lift the paper. So let's explain the phenomenon a little bit more quantitatively by analyzing the motion and separating it into steps. The first step is the free fall of the ball on the ruler from a height h and no initial velocity. The second step is the collision of the ball and the ruler, where the ball hits the ruler with a velocity of v1, which is given by this formula here on the right. The third step is that the ball bounces off the ruler with a velocity of v2, and the coefficient of restitution for this particular motion is given by the formula that you can see here on the right. So we can calculate the change in velocity during impact, which is given by this formula. And by this formula, we can calculate the impulse J. And knowing the duration of the collision, which we will calculate experimentally, we can calculate the maximum impact force that the ball has on the ruler, which is given by the formula that you can see here. So the second approach for our quantitative analysis is that we establish a natural frequency for the system of the two bodies, and then the total impulse J will be given by this formula, and then the impact force will be given by Pj times F, the frequency, and combined, if we know the frequency, we can calculate the impact force. So using the first approach, if the force acting on the paper is F ATM, which is atmospheric force, which is equal to P times S, where P is the pressure and S is the surface area of the paper, then for the phenomenon to proceed, we need the F impact maximum. When the F impact from the ball on the ruler is at a maximum, we need it to be less than the atmospheric force. And this is because the paper rests on the table upon the ruler, and upon a sharp strike on the free end of the stick, the air cannot go under the paper quickly enough to compensate for the atmospheric pressure on top, so air cannot get under the paper, which acts as a vacuum. So we need the F impact to be less than the atmospheric force. So we can also get the formula down here on the right in order to obtain a theoretical model. So using this formula, we can calculate the minimum surface area of the paper for a given ball mass and initial height, and show the relationship between the independent parameters of our experiments, which are the mass of the ball and the surface area of the paper. So moving a bit further, we see that the problem statement suggests that the ball bounces off the ruler without breaking the ruler. We can use this model here to calculate the maximum torque for the ruler not to break, which is the following here. And in our experiments, we ensure that the ruler will not break by using a steel ruler. These are the parameters of our experiment. We have the independent parameters, which are the ones that change during our experiments, which are the ball mass and the table, which you will see I will explain later. The dependent parameters, which are the ones we measured, are the paper size, so the surface area of the paper. The control parameters in our experiment are the ruler placement, the ruler material, and the height of the ball toss. So let's continue with our hypothesis. We have two parameters. First one is the hypothesis for the table. This is based on our qualitative analysis, and we see that if we conduct the experiment on a table with holes, air will be able to get underneath the paper and the phenomenon will not proceed. And the second hypothesis for the ball mass is that using the theoretical formula, we will be able to calculate the minimum surface area of the paper for each given ball mass. As the mass increases, the surface area of the minimum surface area of the paper will also increase based on our theoretical model. This is the ball release mechanism that we used for our experiment in order to make sure that for each given toss, the ball will not have an initial velocity or an initial angular momentum. And this is the mechanism that we used to prevent any human errors in this experiment. This is an apparatus of the materials that we used. You can see here the balls that we used, of course, the mechanism that I showed you earlier, the ruler, the paper, and the other things that we used in order to capture the experiment and make the videos using Tracker. So the first experiment, we had the hypothesis that if we conduct the experiment on a table or on a surface that has holes, the phenomenon will not proceed because air will be able to get underneath the paper. And you can see that this is confirmed. You can also see the video on the right here. Here we have a surface that has holes. I don't know if you can see it. But since air is able to get underneath the paper, the phenomenon will not proceed. And you can see that this is valid. So our first hypothesis is confirmed. On to the second experiment, we have here the height of the toss. We are doing the experiment. We take a video, we put it into Tracker, which is a video analysis and modeling tool. And by Tracker, we measure the duration of the collision. And then we can calculate theoretically the minimum paper surface area. And then we compare it with the experimental paper surface area that we found from each given ball mass and experiment that we did. By doing this experiment, we obtain this table right here, which we have each ball mass, the collision duration, which is taken from Tracker, the theoretical surface area of the paper, the experimental surface area of the paper, all in cubic centimeters, and the percentage of error for each given ball mass and each given trial. Here you can see some videos for some masses and then some graphs taken by Tracker, which are the velocity and the distance from the ruler for each experiment. And here is the graph that we took for each mass and then paper surface area on the y-axis. And we can see that as the mass increases, the minimum paper surface area also increases. We have with the black the theoretical values and with the red the experimental values. The theoretical values are obtained from the theoretical phenomenon, from the theoretical model, and the red scatters here are obtained from our experiments. So let's analyze a little bit what is happening here on the left, because you can see that the theoretical and experimental values diverge from each other. So let's see what is happening. The minimum experimental value of the paper in our experiment cannot be less than approximately 45 cubic centimeters because the paper must cover at least the surface area of the ruler. I think this makes sense because if the paper does not cover the surface area of the ruler, the phenomenon cannot proceed any further. So if the paper is less than covering the surface area of the ruler, the phenomenon cannot proceed. So because the ball masses here were very little and the theoretical model found values that were less than the actual surface area of the ruler, we were not able to obtain correct results from experimentation. And this is why we have a divergence here on the graph on the left. So the second hypothesis is indeed confirmed because for the mass that increased, the surface area did actually increase. The theoretical model, as we said, does not apply when the calculated area is smaller than the area of the ruler. And we have that the average error of all the values is 23.09%, which is kind of high. But the average error for the values where the theoretical model actually applies is 5.43%, which is actually a small error and makes our experiment valid. So we see that the average error is 5.42%. Some error analysis, we know that some errors might be attributed to the accuracy of the duration of the collision, which was obtained by Tracker. And the videos were in slow motion, so the accuracy is higher, but there maybe was an error there. the accuracy of the coefficient of restitution value, which was obtained by bibliography, and the accuracy of the theoretical velocity calculations. So let's summarize the report a little bit. First, we explained the phenomenon qualitatively and then moved on to develop a quantitative theoretical model that predicts the relationship between the mass of the ball and the minimum surface area of the paper for each given height. We talked about the parameters and hypotheses of the problem and explained the experimental setup that helped us reduce human errors. Then we analyzed the two experiments that were done and presented the data acquired. Lastly, we talked about the possible errors of the experiment. So that summarizes our report. And here are the references that we used for our research. And thank you very much for your attention.